Welcome to ML Theory meeting. So today we will have Tom Jacobs, and he will talk about his work, which is the title, which is like the weight decay control implicit regularizations, and some insight on generalization and sparsity. So Jacob is a PhD student at the CISPA Helmholtz Institute in Saarbrücken, Germany, under the supervision of Rebecca Berghaus. He's currently working on understanding training dynamics in deep learning and design methods for efficiency. Before that, he has graduated with a master in applied mathematics, specialized in mathematical analysis and probability theory from the Technical University of Eindhoven in Netherlands. So the floor is yours.
Yes, thank you for this introduction, and also thank you everyone for joining. So I'll need to talk about how weight decay controls implicit regularization. So this is in contrast what weight decay normally is associated with explicit regularization. So as an explicit control over the model capacity. And so we will highlight that it also has an implicit effect, and this implicit effect then I will use to improve generalization and also use to induce sparsity in models. So first, give a quick overview of this talk. First, I will introduce some background on overparameterization and implicit regularization, and how overparameterization actually induces this implicit regularization. Next, I will give the main, the contribution of my work is how weight decay actually influences this implicit regularization. And finally, I will give two applications to improve generalization and sparsity. So yes, let's get into it. So overparameterization first. This picture shows double descent. On the x-axis, you can see complexity, so the size or width or depth of a neural network, for example. And on the y-axis, you can see the error. And from classical statistics, we would suspect that if one has a very huge model, we would overfit on the training data, and then you would not have a good generalizable model, and the test error therefore then starts increasing. But we wouldn't be here if deep learning wouldn't solve this. So in deep learning, we actually can increase the model capacity and actually decrease the test error. So why is this the case? This is a long line of work that tries to answer this, and this is covered by this umbrella term implicit regularization. So first, we have to define what I mean by overparameterization. So there's two forms of overparameterization, I would say. Macro overparameterization, which can be seen as like increasing the width or depth of a neural network. Think of anti-K regime or mean field limits. But there's also a different type of overparameterization, namely what I would call micro overparameterization. So this would be the interaction between layers or between groups of parameters. So this is also highlighted in this figure, where the macro level would be like the full neural network or transformer block, and the microdynamics would be like the interlayer dynamics. So two examples of microdynamics, which we will focus on, are, for example, in an attention layer, the interaction between the K and the Q matrix, or the key and the query matrix, and, for example, also in LoRA, where you have an A and B matrix as also a product structure of two matrices. So yes, so this overparameterization induces a so-called implicit regularization. And to study what this implicit regularization is, we first have to introduce the setting. So consider training an objective function. So this is like a loss function with the neural network, for example. And X are the parameters of this neural network. Then we train this with, say, gradient descent, which is the backbone of neural network training. And we now, in addition, we also take the learning rate super small, and then we can study so-called gradient flow. And this is just to simplify the analysis and to motivate this. I will highlight this in an example. So in this figure, you can see gradient flow and gradient descent initialized at the same point. And then they converge towards a point on this green line, which is a zero loss set, and then they converge to very close solutions to each other. So we are we can actually study this gradient flow and then make predictions with this on what would happen in more realistic settings. So to highlight this overparameterization or micro overparameterization, we will use this example, the product overparameterization. So this is a product of two parameters, say M and W, and we want to study what the effect is of this type of overparameterization. So now the gradient flow becomes this, and this is just applying the chain rule. And so if we differentiate with respect to M, the W drops out. And if we differentiate with respect to W, the M drops out. So we can study this dynamical system or gradient flow system. But we actually want to know what happens to this X variable. So can we study the dynamics of the original variable X? But in order to study this, we first have to introduce a so-called mirror flow, which is a generalization of gradient flow. So consider a function we will now refer to as the Legendre function R. And for gradient flow, this would mean this Euclidean distance between the initialization and the input value X. And so this leads to dynamics. So on the left-hand side, you can see the gradient flow that corresponds to gradient descent. And then on the right-hand side, you can see a mirror flow. So this is the gradient with respect to this Legendre function. So you can see that if you take the gradient with respect to the Euclidean distance, then you get a gradient flow back. And one important property of this Legendre function is that its global minimum is centered at the initialization of the neural network. And we will see later why this is important. So an example, these mirror flows can have wildly different solutions than the gradient flow solutions. So for example, here, the mirror flow leads to a sparser solution. So you can see that now at the same initialization, the x1 coordinate is way larger than the x2 coordinate. And so this we can use mirror flows to steer the dynamics, but it also turns out that these overparameterizations actually correspond to a mirror flow. So this product parameterization actually can be studied using this mirror flow dynamics. And this map then now depends on the initialization of both this M and W. So for example, if we have M is equal to 0 and W in a small scale, then this map corresponds to a sort of L1 function. While if W would be large, then we have an L2 type of function, which would roughly correspond to the gradient flow setting, which would also correspond to the Euclidean map. So we have two types of regimes, so small scale and large scale. And the large scale would correspond to overfitting, while the small scale would lead to feature learning or better generalization. But this already highlights that even though we have overparameterization, we can actually induce better generalization. But now this depends on the initialization scale. So to highlight this is a result for linear regression. So if we have this overparameterization, so this M times W overparameterization, one can show that for linear problems, one actually goes to the solution of this Legendre function. So one say we have a sparse ground truth that corresponds to this that is generating this data, for example. Then one can recover this using this type of overparameterization. So one actually can do feature learning instead of overfitting on the training data. However, there's one caveat. We have to initialize at 0 to actually induce sparsity. So this might not be realistic actually in deep learning, while we just do random types of initialization, for example. So to recap, we want to study the microdynamics or micro overparameterizations with some reparameterization G that depends on some variables W, and we want to minimize still this loss objective F, which is a loss function plus some deep neural network. And we then want to study the gradient flow of this W, and this in turn can be then under some assumptions can be studied in the original variables X using a so-called mirror flow. And we will use this product structure as the main example throughout the talk. So now we know what implicit regularization is and how it relates to overparameterization. So now I will include how weight decay actually controls this implicit regularization. So what is the challenge here? So under some nice assumptions on this reparameterization, one can show that the mirror flow, well, X satisfies this mirror flow, or this reading flow turns into a mirror flow in X. But now we have a penalty term, say H, which can be weight decay, for example. But this needs to be integrated under sufficiently nice assumptions on H and G. And so what we did, we derived these conditions under which G and H satisfy nice conditions, and then we can integrate it into this mirror flow. And then we can study how this changes the dynamics. And this is based on the work recently published at ICML. So the main result is given in this theorem, but the main takeaway should be that now this Legendre function R becomes dependent on the integral over the total amount of weight decay applied. So one can now control how this map looks like. And in addition, we can have a geometric interpretation, which we'll later use to prove convergence and optimality towards some solution, just this linear regression problem. So to highlight this again in this product structure, what we now can do is we can, while applying weight decay, we can move the Legendre function from L2 shape, so from A very small to like making A very negative to the L1 mirror map, and effectively inducing sparsity or feature learning. In addition, as I mentioned before, the Legendre function is centered at initialization. But now, using weight decay, we can actually move the center towards 0, which can be very useful for inducing sparsity, as we see also later. In addition, we can control how close we will be to L2 or how close we will be to L1 using the strength of the regularizer. So to summarize what this means also for other reparameterizations, we can control the type of bias, so L2 or L1, low rank or full rank bias, and also we can control the center of the bias. So for example, we can move it towards 0, and in addition, which I will not cover in this talk, so-called range shrinking effect. This means that the Legendre function shrinks the potential solution set of what we can reach during the training. But this is more on the theoretical side that might not occur in practice. So I will focus more on the latter two. In addition to this mirror flow, one can also describe these training dynamics using so-called Riemannian flow. These descriptions are equivalent if this Legendre function is twice differentiable. And then we can see, we can use this to prove convergence for so-called Bachmann functions, which are slightly stronger condition. And moreover, if we turn off regularization, we can recover this optimality result for Legendre functions. So now we actually converge towards a sparser solution in, for example, this product setting, when if you turn off the regularization, one can show this optimality. Well, suppose you keep the regularization on, you would converge to a solution that at least has this penalty term still explicitly there. And so we can exploit this, as you can imagine, to go to more optimal solutions. And so now that we know how to integrate weight decay with this implicit regularization, I will give some applications towards generalization and sparsity. I'll first focus on generalization. And so what is generalization? It is effectively, can we make predictions on unseen data? So on a test set, validation set. And in order to, the main application would be making them useful for practical applications. And the main underlying question for this line of work is how can we improve this model prediction? And as I said earlier, we can perhaps improve this by turning off the regularization at a good time during training. And so we consider linear regression or matrix sensing, which is a type of linear regression which is normally used in these theory settings to show the effect of implicit bias. And what we do is we train with and without a product structure. So we will overparameterize with two matrices, or we will just train a single matrix. And we then apply weight decay to the product structure, and we apply L1, or like a linear lasso, to the linear term to induce sparsity. And as you can see, we will turn off the regularization at the black line in the middle. As you can see, the product structure has now, if you turn off the weight decay, you can get a way lower reconstruction error, so effectively recovering the ground truth if you turn it off. While if you would have a linear parameterization, one does not change the type of bias, and actually we will just overfit on the training data. So this shows a benefit of using overparameterization, and also a benefit of turning off the weight decay. Well, if you would keep it on, then you still get the same or similar reconstruction error as you would have if you have not even turned on weight decay at all. So this theoretical setting, we then also use as motivation to study LoRA and attention. So we get some similar insights on transformers and LoRA, with some caveats, of course, that these are trained with LMW, but still we can get similar insights in the sense that we can turn off weight decay in some part of time, and we can track the relative sparsity, so the nuclear norm. So this is the L1 norm on the matrix, and the Frobenius norm, which is the L2 norm, and then we can show that if one turns off the weight decay and have the similar total regularization strength, so this integral over A, or this A value, then it has been better to turn off the regularization in the end. And then for the similar sparsity level, so at these points where these lines intersect, then we would have better model performance in these cases where the regularization has been turned off compared to when the regularization has been kept on. Yes, so the main takeaway from this is we can control this Legendre function. So one can control the position, one can control the type of bias, and also this range shrinking effect. And moreover, it has a lasting effect. So one can actually turn off the regularization and still keep all the benefits from the regularization. So it has a lasting effect. And this can, of course, then lead to better regularization strategies by taking into account that this implicit bias is actually changing during training. And also, yes, studying the training dynamics by integrating this into this mirror flow framework. Okay, so the second application is sparsity. So first, get some background on it. Why would we care about sparsity? Given the large size of neural networks or large language models, we would like to have to compress them for cost saving effectively, and also for inference time, because it will take longer to run inference on larger models. So if you can compress them using less parameters, then we can save a lot of cost. Also, do we actually need all these parameters? Most likely not, given that we are usually overparameterized. So one can actually do this. So there's two lines of. The main challenge would be to find the sparse neural networks, and then under the caveat, of course, that we still want to keep model performance high. There's two lines of work on this, so-called continuous sparsification and iterative sparsification. Continuous sparsification is as you might guess, based on reparameterizations, which conveniently corresponds to this mirror flow setting. So this is product structure, for example. And then the other one is iterative sparsification, where you would actually just train normally, for example, and then prune according to some criterion, a fixed amount of weights, and then you retrain again, and then so on and so on. So these methods could be complementary, actually. And so we will focus on this continuous sparsification, and this is based on the work also recently published at iClear. Again, recall this product structure. We can use the change in the Legendre function due to regularization from L2 to L1, since you might want to have, if you want to sparsify, you actually want sort of dense training in the beginning of when you start training. While in the end, you want to end up with a sparse model, but you don't want to sparsify in the beginning because this might hamper generalization performance. And also, we can control the strength, which means we can control also the sparsity level in a more convenient way. Now we actually use this product parameterization, so plus weight decay, to sparsify a neural network. So we actually replace an in-place replacement of, say, a ResNet, and we replace every parameter with m times w. And then we can actually sparsify the model using this technique. The main innovations of the algorithm are that we can now, based on some criteria, such as the training accuracy and the sparsity level, we can tune the regularization. And we also know, since the Legendre function is lastingly changed, we can turn off the regularization gradually at the end of training. And to ensure that we start in an L2 setting, so that the method actually has a dense training phase, we initialize this m0 squared minus w squared, 0 squared, to equal to some constant. This ensures that if this constant is large enough, then we are still in the L2 regime. And so this leads to, so this first thing about the initialization already leads to improvement over a previous method that also uses this product structure, so-called spread. And this method initialized in the sparse regime, and this leads to the inability to move through zero. So one can actually not, if one parameter needs to be an opposite sign, then one cannot move it's very hard to move across this barrier, even though, and then everything gets stuck. And in linear regression, this is very present or made very clear. One cannot reach the ground truth if you have opposite signs. So while pilots would reach the ground truth very fast, the spread method can't come close. And similarly, just the L1 penalty could still reach reasonably close to the ground truth in this linear setup. And so with this method, we do a one-shot experiment on standard vision benchmarks, and we show that we are better than all the other continuous sparsification methods. And also we show that just the initialization is already good enough to perform better in the medium sparsity regime, so say 80% sparsity, 90% sparsity. While in the high sparsity regime, spread still can outperform, or the other method called STR can still become competitive. And in addition, we conduct an experiment on ImageNet, and we show that we are competitive in the medium sparsity regime, while so for like the 80-90% range, and for the high sparsity regime, so above like 95% sparsity, so only 5% of the parameters are remaining, we are very much outperforming the other continuous sparsification methods. So the main takeaway is from this is that we can turn off the regularization in the end of training, and therefore keeping all the sparsity, and also we can move from L2 bias to an L1 bias, and therefore gradually sparsify the neural network. Yes, so also thank you for your attention, and also thanks to my co-author and supervisor, Joe and Rebecca. And so if sorry. So if someone is interested in the papers, put QRs on the screen.
Thank you.